Okay, in this video we're going through the radius tangent theorem. Now to understand this one we need to know what a radius and a tangent is, so let's have a look. Radius you're probably familiar with already, and it's the line from the center of a circle out to the circumference. Just keep in mind it only goes halfway across, it's the diameter that goes the whole way across. A tangent is a little bit more tricky. It's a line that just touches the circle at a single point. So if I draw a line over here, that is not a tangent because it doesn't touch that circle. If I draw a line cutting through the circle, that is not a tangent. But if I do just draw a line that touches it at a single point, yep, that thing is a tangent there. So just keep all that in mind when we're working with this theorem. So let's have a look at the theorem itself. We're going to jump over here, and it says the tangent to a circle is perpendicular to the radius at the point of contact. So basically, you draw yourself a line from the radius out to the tangent, and you've got yourself a tangent there. What the theorem tells you is that is a right angle that you get between those two. And that's what the word perpendicular means. It means right angled. Okay, so let's use this theorem on a couple questions. Find the angle OAP. The angle that they're looking for is this angle right in here. And angle OAP equals 90 degrees by the radius tangent theorem. Next, find the value of theta. So theta is this angle sitting right in here, DAB. And we want to look at how do we get this one? So there's a few things going on here, and we can jump back to figuring out what all three angles are in this triangle from a previous lesson. So let's jump straight back to angle in a semicircle theorem, and that tells us that in a situation like this, we get a right angle up here. So we're going to be using that, and that gives us a right angle up here. So angle ABC equals 90 degrees, and that's by angle in semicircle theorem. Great. Then that tells us what this angle is. So let's just call this angle like alpha. So let angle BAC, just to make things a bit quicker for ourselves. Then we know alpha plus 90 plus 52. All those three angles would have to add up to 180 by sum of angles. And this is sum of angles in the triangle ABC. Great. Therefore, let's see, 90 plus 52 would give you 142. So I believe that tells us alpha has to be 38 if you rearrange that and solve it. Okay, great. So we can replace this thing here with 38. Now, alpha plus theta would all have to equal, let's see, that is the angle DAC. And we already knew that alpha was 38. And that's going to give us 38 plus theta equals, well, angle DAC has to be 90 degrees. So the angle that I'm talking about with DAC is sort of like that angle in there. And as angle DAC equals 90 degrees, this is because of the radius tangent theorem. Great. Therefore, theta would have to be, let's see, it would be 52 degrees once you solve that equation. So we'll step out exactly what we did here. So we first figured out this triangle. We knew that was a right angle from a theorem from a couple lessons ago. And then the right angle plus 52 plus whatever this angle is was 180. That tells us this angle is 38 degrees. Now that we know that, we know 38 degrees plus this yellow angle here would have to add up to 90. So that missing angle would have to be 52 degrees because that would make it work. All right, next one. AP is 2 and the radius of the circle is 3. Find the exact length of OP. Now, when you see something looking for a length, you're usually going to be using Pythagoras. So that's where we're going with here. First thing we're going to do is say OAP equals 90 degrees by radius tangent theorem. There we go, 90 degrees right in there. And then we can label these. So AP is 2 centimeters, and it says the radius is 3. So then this length here is 3 centimeters. You might be tempted to say this length here is 3 centimeters, but it's not, because only the length from O out to the edge is 3 centimeters, and that's not really going to help us at all. So we want to find that missing link there, basically. So the best thing to do is to take a triangle out of context. So just draw it off to the side here and make sure all your letters line up. So we've got O here, P here, and A here. We also know this is right angled, so we're going to be using Pythagoras. That length is 3, that length is 2, and we don't know what that length is, but we know it's a hypotenuse, so we're going to call it C, and we'll just call that one A and B. So we're going to get A squared plus B squared equals C squared, and this is going to be Pythagoras on triangle OAP. Then A is, well, it's 3, and B is 2, and C we don't know. But this is 9 plus 4 equals C squared, so C squared would have to be 13. Therefore, C equals plus or minus 13, plus or minus root 13. Now, you could get plus root 13, you could get minus root 13, but we know C is the positive version because we're talking about lengths here, and in the real world, lengths cannot be negative. All right, great. And this is in centimeters. Now, the question asks for the exact length of OP, so we're actually done here. If the question did ask for an approximate, this is what you would do. You would go to your calculator and you would type in square root of 13 to that. So you get the square root sign, 13, hit enter, and it's 3.606 centimeters. So just to be clear, this is the exact answer, and this is the approximate answer. The question asks for exact, so you'll give the top version. Find the exact value of theta here is our next question, and there's a few things going on here. So let's break it down bit by bit. We're going to do the exact same process that we did for finding this angle in here, noting that this is a right angle. So angle ACB equals 90 degrees, and that's from the angle in a semicircle theorem that we saw before. Great. Therefore, 29, well, angle ABC plus 29 plus 90 would all have to equal 180. And this is sum of angles in the triangle ABC. So yeah, all three of these angles, so that one, and that one would all have to add up to 180. Great. So angle ABC plus 29 plus 90 is 119, 180. So that looks like angle ABC would have to be 61 degrees. Cool. Okay, so now that is 61 degrees. That's good news. Now here's where the question gets really tricky. You have to note that this triangle here is isosceles. Now the reason that's true is because this is a radius of the circle, and this is also a radius of the circle. So that triangle OBC is isosceles. Now, what do we know about isosceles triangles? Well, the definition of an isosceles triangle is that it has two sides which are the same length. We draw them in with that single line to show they're the same. And then something that we know about isosceles triangles is that these two angles, here and here, are the same angles. Really important to use in our theorems. So let's use that here. Therefore, well, this angle down here would have to be 61 degrees as well, because they have to be the same. So basically, we could write that in as angle OCB equals angle OBC, which is 61 degrees. Because triangle OBC is isosceles, as OB and OC are both the radius, or both radii, depending if you want to pluralize that. Great, so that's 61, and then the last bit is just similar to that bit we did before. So we know this whole bit is a right angle with the radius tangent theorem. So we're going to get 61 plus theta plus the angle OCE. No, 61 plus theta equals the angle OCE. Which is 90 by radius tangent theorem. And then you're going to have to rearrange this. So you could take 61 from both sides, but either way, you're going to get theta is 29 degrees, just like that. And we're done. We found the value of theta.